Hi everybody, welcome back to our political statistics class. This is the sixth lecture and this is the sixth week and we're almost done with our class. And I really want to congratulate you for a very good job, on a very good job during these 6 weeks, six past weeks. We have learned a lot, but we still need to learn much more. So buckle up because this week and this lecture in particular, we're going to learn a lot of things. But that's going to be very useful for you guys for preparing the final report of the applied project and for actually learn how to use statistics in a meaningful way for your careers. Okay, so let's move on. So as I said, during this week, we're going to learn how to use different methods, statistical methods, inferential methods of analysis, and we're gonna be as in those action films in which there are some weapons room in which the people or the main character is told something like you go there and learn how to use these arms and use them or pick whatever you want, something like that. This is actually from the Kingsman film that I like. And you're gonna be able to use those arms to struggle with whatever kind of research question you have in mind. Okay, that's my goal. My goal is to equip you with weapons that help you to solve research questions that are meaningful for you guys. Okay, and these 2 weeks whatever we're gonna do, we're gonna be thinking all the time on the applied project. So you learn, like, I think on this lecture, how can I use this lecture to prepare my applied project? Okay, so you're gonna learn in the technical part, for instance, how to prepare cross tabulation, because we learned just the basics, how to prepare like a two-sides table, but we're gonna learn how to use 3 variables in a table, and we're gonna learn how to prepare figures with 3 variables. So everything that I'm gonna teach you is gonna be useful for the applied project, and actually I'm gonna ask you to do things or to try to advance whatever you can with your applied project. Okay, so let's take a very brief summary of what we learned in the past. So remember that we learned about threats to external validity, and those threats occur when you want to say something about the population based on the estimation of statistics of the sample or a sample drawn from that population. Okay, that's when we face these threats to external validity. Okay, so we learn also these concepts of measures of central tendency and measures of variation, and these ideas of the shape of the distribution, and we use all that knowledge and put it in the last week. And the last week was heavy conceptually. So you learn how to use this idea of the random sampling error, that is this good error. We want that error instead of the systematic error because we know how to deal with this error. We know how to measure this error. So we embrace the uncertainty related with this error. Okay, and we learn as well a little bit about this central limit theorem and how to use the normal distribution and the student's t distribution to make inferential or probabilistic inferences about the population, right? That's the foundation of inferential statistics. So this class, we're gonna learn how to use all that knowledge and apply it to something new, something that is called tests of significance and measures of association. And the final week, hopefully, that's my goal. But I will see if we feel comfortable with the knowledge that we are getting to move to the final part of the course, that is linear regression. And linear regression is very powerful because it not only allows us to deal a little bit with the problems of external validity, but also it allowed us to deal with the problems of internal validity that we have just left aside to some extent. But when we learn descriptive statistics, especially the second part of descriptive statistics, when we control for a third variable, So we were thinking in terms of the threats to internal validity. Okay, so linear regression allows us to tackle both kind of uh, threats to inferential analysis. Okay. Okay, so this is the roadmap of today. I'm gonna introduce you uh, the logic of bivariate analysis, what is statistically significant and what is substantial or substantive significant. And we're gonna learn 6 different methods. So again, buckle up and try to think or try to process or try to think this class as I said, like I'm gonna give you a brief summary of all these methods. I'm not gonna focus on the mathematical part. I'm gonna give you a little bit of sense how are the formulas and the mathematics behind of this, but my emphasis is gonna be in the assumptions and how do you interpret these methods, what are the limitations of these methods, if any, and how to conduct and interpret each method in R. Very quickly, I'm gonna show you how to do it, okay? So don't worry about the mathematical part because it's not gonna be the emphasis and never has been the emphasis of this class, okay? Okay, so let's move on. So the point of departure, as I said, is the inferential problem. So for instance, remember, I don't know if you remember this example from previous lectures. So we were talking that we have this hypothesis that women had a mean feeling thermometer higher than men in terms of immigrants, right? And we estimated this hypothetical example and we said, okay, the difference is of just 3 percentile points. The key question for us right now is, okay, we know that. To what extent that difference actually reflect what happened in the real population? And remember that this real population is with huge quotation marks. Huge, okay? So we are saying that that population is actually theoretically created or something like that. But this is important to try to reach like a rigorous scientific results, okay? So we have this idea to what extent this difference reflect the true difference in the population, okay? We're gonna use something that we learned in the previous class, this idea of the standard error or the random sampling error. Because this problem of the random sampling error or standard error is gonna be present all the time when we want to move from the statistics that we estimated about the sample and we want to say something based on those statistics to the population of interest, okay? There's always going to be an error. There's always going to be uncertainty, okay? Another thing that I want to highlight here is why we're focusing on a difference. And a difference is important, it's a good point of entry because to some extent in every hypothesis we have a comparison between different groups and at least between 2 groups. We are saying that one group experienced something that we call X or the certain values of X, and we expect that that group is going to have certain other characteristics which are other values of Y in comparison with another group that didn't experience that X, okay? And here these terms related with experimental kind of research design are very useful. So we talk about this treatment group. Treatment group is this group that experience something, so certain value of X, for instance, I don't know, a new drug or a new treatment or a new policy or whatever, and a control group that didn't experience that. So we expect that the treatment group is going to have certain value of Y. For instance, if it is a drug, it's going to be that person is going to be healed of, I don't know, of cancer or whatever. Okay. So there's always going to be this comparison between 2 groups. For that reason, we're talking about differences between sample means or sample proportions or so on. Okay. Okay, so the first thing that we need to tackle when we are doing when we are conducting inferential statistics is to debunk this thing called the null hypothesis. The null hypothesis states that there is no real difference in the population. If we are talking about, again, that feeling thermometer about immigrants between male or men and women, the null hypothesis that states there is no real difference in the population, and what you are observing in the sample occurred just by chance, just because there was a certain problems or just for random processes that you don't know when you were drawing the sample. For that reason, it's a random sampling error. Okay, so the null hypothesis states that. In other words, the null hypothesis said that if you subtract the value of men to women, the result is going to be 0 instead of 3. Okay? We want to debunk that hypothesis, and we want to say, because our hypothesis is that women tend to be more supportive of immigrants than men. So we expect that the difference between women and men feeling thermometer is going to be higher than 0. Okay? And what we want to do when we are conducting inferential statistics is that we want to make correct inferences. Okay, we want to debunk that hypothesis, but we want to do it in a way that is correct, that we have strong and rigorous evidence that we can reject that hypothesis. So we want to avoid two types of error. The first type is the most dramatic in in scientific research, and is when the null hypothesis is actually correct, but we incorrectly reject it. Okay, that's a huge problem in science. The other is less dramatic, but it's not correct. So, and it is when the null hypothesis is incorrect, but we don't reject it because maybe we don't have enough evidence, or for any reason we were not able to reject it, even if the null hypothesis was wrong. Okay. So how do we avoid to making those errors, type 1 error and type 2 error? The way we do it is that we assume that hypothesis 0, or the null hypothesis, is correct. We embrace uncertainty, and what we want to do is to use a high threshold, very rigorous threshold, to reject the null hypothesis. We want to say, if the null hypothesis is likely to be true in a more than 5 times, or 5 out of 100 times, we can reject it. Or in other words, as I have here written, the only way that we're gonna feel confident to reject the null hypothesis is if the likelihood of that the null hypothesis is correct is smaller than 5%. Okay, and this is going to be clearer as we advance with the 3 types of significant tests that I'm going to teach you during this lecture. Okay, so the first type of test is called the test statistic, or t-test, and is usually used to compare two sample means. Okay, so the first assumption and the first prerequisite that you need to have in mind when you want to use the t-test is that your dependent variable needs to be numeric. Okay, it needs to be in an interval level or in the ratio level. Okay, look at this example. So we have here the GDP per capita, and we group all the countries of the world by different levels of the GDP. That's our independent variable. So we have from low to high levels, and we have as dependent variable the mean score freedom house. Okay, our hypothesis is that developed countries tend to be more respectful of civil liberties than their developing counterparts. But we're gonna focus here to say that our hypothesis is strong. We want to focus just on the difference between medium low and medium high countries. That 0.9 difference, okay? And we want to know if that difference is statistically significant or not, okay? Because it seems to be small, right? It's just 9.9 points in the scale that goes from 1 to 12. Is that significant? We will see. So to estimate the t-test, the first thing, there are like three methods, okay? The first method is using, or you can use the confidence intervals. And what you do is that you find the standard error for each mean, each sample mean. For instance, in this case, and I'm not gonna do all the, or I'm not gonna conduct the mathematical procedure here because we don't have enough time, and I taught you how to do it in the last lecture. But the standard errors of for the sample of the medium low countries was 0.25, and for the medium high country was 0.30. Okay. Later we find the confidence intervals for each mean. Okay. Remember that the confidence intervals are that range of values that we feel confident that the true mean in the population will be. Okay, so it's gonna be from 6.5 to 7.4. Okay, and the mean that we estimated for this sample was 7. So we have that range from the lower to the upper boundary of confidence. Okay, and we do the same with the medium high countries. And what we want to do is to like see, and we don't want these different values to overlap. If they overlap, we feel less confident to reject the null hypothesis. But in this case, they don't overlap. You can see it here. Okay? I'm going to show you this graphically. So we can reject. In this case, we can reject. Let me show you graphically how this is seen. Something like this, right? So you have here, this is the medium high, and you have the lower boundary is 7.5, and the higher or the upper boundary for the medium low countries is 7.4. So there's no overlap. And we can see that there is a not huge, but an important difference between the two sample means. Okay, again, so we can reject the null hypothesis with this information. The second way to do it is actually to use the test statistic. The t-test uses three values: the expected difference according to our hypothesis, or the alternative hypothesis as it is called, minus the expected difference of the null hypothesis, which is 0 always, divided by the standard error of the difference of the means. How do you estimate the standard error of the difference of the means? Well, you first square each mean of the random sampling error. Later, you sum the square mean of those random sampling errors, and later you take the square root of them. And our standard error is going to be here 0.31. Okay. And later we plug those numbers here, and we're going to find the test statistic. Okay. So something that is important to keep in mind is that the t-test, the result of the t-test and the result of all the significant tests are expressing values of standard errors. They could be z-scores, or they could be t-values, or they could be chi-square values, or something like that. Okay? So now we're going to understand better how do we use these z-values or t-values. Remember that they are standardized ways to present different scores in a normal distribution, or not a normal necessarily, in a distribution. Okay? Okay, for interpretation, it's important to know that we can use the z-values if our distribution is normally distributed, or we can use t-values when that distribution is not necessarily normally distributed. Conventionally, for the comparing two sample means we usually use the t-values, okay? Remember that the t-values or the student t-distribution is affected or is intrinsically related to the degrees of freedom of the sample. And in this case, or of the other statistic that you're going to use. In this case, to find the degrees of freedom of the difference is equal to the sum of the size of the samples minus 2. So in this case, it's going to be 90. And you can check those values later if you have time or you are interested on that. Okay? Okay, so we're going to use now, as I said, you can use the C values or you can use the T values depending on whether this distribution is normally distributed or not. For the sake of the explanation, I'm gonna say that this is a normally distributed kind of distribution, and so we're gonna interpret with C values. Okay, so for this example, the t-test yield a value of 2.9 standard errors. So what does it mean? Okay, so we said, remember, that we can reject the null hypothesis if it is a very unlikely event, less than 5%. So remember how to use the normal distribution to make probabilistic inferences about the population. So remember the C value, okay? Just a little bit. When the C value equals 0, that means that we are in the mean of that distribution. The peak of that distribution means that this is the most expected event to occur, okay? For that reason, most of the data is here because it's the most likely event to occur. So when we move from that 0 in the C-score to number 1, number 2, number 3, or -1, -2, -3, an event is going to be less likely to occur, okay? So the higher the value of C, the better for us, because we want to reject the null hypothesis, okay? So again, remember this, most of the data or most of the scores of our distribution in a normal distribution will be within more or less 1.96 C values, okay? Look at here. So it's going to be here, almost 2, or say 2 C values, okay? What does it mean? It means that only 5% of the events will be likely to occur with values higher than 1.96 or 2 C values, okay? So if the null hypothesis is correct, it might be smaller in C values than 1.96. For instance, if the C value is 0, that means that the null hypothesis is a very likely event to occur because it's here. Do you get it? Actually, for this case, the C value was 2.90. Look where is 2.90 positive value. It is here. So it's a very unlikely event. Certainly it is very close to 0, okay? Do you get it? So remember that if you are in this part of the distribution, this is because this is the most likely event to occur. If you are here, this is more likely to occur than if you are here, right? Or if you are here, okay? Okay, so let's move on. That's the C value. So in summary, we want high C values, because if we have high C values or T values when we are conducting this significant test, that means that the probability that the null hypothesis is correct is very small or almost unlikely, okay? There is another concept that is, or not a concept, a statistic that is very important that you learn right now, and is the p-value. The p-value is intrinsically related with the C value. It's the opposite to some extent to the C value. The p-value is the actual area under the curve of the normal distribution or a distribution. It is the actual probability that the event occurs. Let's move here again. So if I'm here, the p-value is going to be, if I'm here actually, and this is the area under the curve, or better, imagine that I don't know. If I'm here, the area under the curve is very small. It's almost nothing, right? If I am here in the peak of the distribution, the rest of the area under the curve is 50% of the distribution. Okay, if this is a normally distributed kind of distribution. Remember that you split perfectly this distribution. You're gonna have 50% here, 50% here. For that reason, when the p-value is here, super high, so you can say anything about the about this, because anything can happen. Okay. Okay, I don't want to make you feel confused, but the important thing here is that you want very small p-values when you want to reject the null hypothesis. Similarly, you want very high c-values because the probability is going to be very low, or you want very small p-values because the probability is going to be very low. Okay. There are conventions in sciences about how to present the p-values. If the p-value is smaller than 5%, which is 0.05, you use 1 star. If the p-value is smaller than 1%, which is very small, it's going to have 2 stars. And if it is smaller than 0.001, which is a very, very tiny probability, you're going to see 3 stars. So the more stars between quotation marks that you see when you run this statistical analysis, the better. We love stars and we want to see those stars, and you can see people talking about the stars. How many stars do you get? I didn't get anything. Oh God. So you really want to have high or at least 1 star. Okay. Okay, let's move on. So that's the second way of interpreting the summary. You need if you want to debunk the null hypothesis, you need high levels of the c values or t values and small levels of the p value. Okay. Okay. So let's move on. The final way to do is, or a final way to interpret the t-test, or to conduct a significant test of two-sample means comparison is the eyeball test of a statistical significance. And again, you use here the confidence intervals. You estimate the confidence intervals of the mean difference. And remember that the null hypothesis says that the difference, or the mean difference in this case, is actually 0. So you don't want to have in your confidence interval 0. You want to have confidence intervals that are higher than 0, or both values, or that are smaller, or less than 0, or negative, the both values. Okay, that's important. In this case, again, we see that we have 0.3 to 1.5. Those are our confidence intervals. For that reason, we can reject again the null hypothesis, because 0 is not there. Okay. Okay, so how do we conduct this in R? So I'm not gonna go directly to the program because we don't have a lot of time, but I'm gonna give you basically the code that I use to conduct this analysis. This is an actual analysis, so you can just replicate it and you can use these formulas for your own analysis with the final project. Okay, so we're gonna use again this CCES dataset, the 2018 version that I uploaded to the lab. So please download it and use it again. And we create this version of the gender variable that is going to be called female. You know how to do that. I'm going to give you the background very, very quick. So imagine that we want to examine the relationship between gender and levels of education in the United States. So we're going to use levels of education as if it were an interval variable, or in other words, a numeric variable. This variable is actually, it goes from 1 to 6. So there's a chance that we can use it as an interval variable and it's fine. And we claim that men tend to be more educated than women, and we estimated a mean difference of 0.3 points. Seems to be very small, right? Do you think that this is statistically significant? Let's see. Okay, so we use this formula called the t-test, and you just replicate it, use it. Remember that I use bold, black letters when I want to talk about a function. I use the green color when I want to highlight variables, and I use the blue color when I want to talk about, or when I'm highlighting objects. Those objects can be, as you know, they can be data sets, they can be tables, they can be plots, right? So that's something that you need to keep in mind. Okay, couple of things. The first one is that, see that education goes first and later goes female. In other words, you always need to write the dependent variable first and the independent variable later. That's an important thing. Okay? Okay. The other thing that is important is that you use this part of the function alternative equal greater. Notice that it's not double equal, it's just one equal, greater. Because we are saying that the difference between the two groups is going to be greater. So the first group is going to be greater than the second group. That's what we are saying here. We can use another instruction such as less. If we say that, for instance, men are less educated than women, or we can use just alternative equal alternative. And that alternative means that men and women are different, but we are not saying in what way they are different. That's called two-tailed test, and it's not very common. We usually in social science said that something is higher or lower or greater or less than other thing. We are not saying they're just different, okay? That's not very common kind of hypothesis in social sciences. Okay, the final part that I want to highlight is that the t-test function is part of R, so you don't need to download any package to estimate it. Okay, so we conduct the test and we find these results. So how can we interpret these results? The first thing that I want to highlight here is the t-value. The t-value, as you can see here, is very, very high. It's 25. Remember, if your t, in order to get your null hypothesis or the null hypothesis to be correct, you need to find a t-value smaller than 2 or 1.96 or something like that, depending on the degrees of freedom. And in this case, you have 25. So you can very confidently reject the null hypothesis, okay? And the degrees of freedom in this case are it's a very high value. It's 55,000, which is incredibly high, okay? Now, the p-value in this case is very small. This part of the statistic that I hated when I first encountered this kind of numbers is E16, which means that there are 16 zeros after the decimal point. Okay, so it's a very tiny probability, very, very tiny probability that the null hypothesis is going to be correct. Okay, the final cool thing about this, let me see. There's another thing that tells you that with 90%, 95% confidence interval, the true difference is different than 0, which is cool.